So in this example, we're going to look at how to do calculations of inference. So a one sample proportion test, the command is prop.test or proportion.test. You're going to put in your X, which is how many you actually measured that had the success, N is how many you actually measured altogether, and then P is equal to what HO says that your proportion is equal to. Then alternative equals either less or greater, depending on what your alternative hypothesis is. If it's your alternative is less, then you'd write less. If it's greater than, you write greater. And if you're not equal, you just leave that sentence, that part off. So as an example, I'm going to go ahead and run this. This is using the Mosaic package again, so I'm going to make sure that library Mosaic is being used. And so if I have n equal to 500 and x equal to 125, and my alternative is greater than 0.22, then I do a prop.test, 125, 400, p is equal to 0.22, and my alternative is greater. Then I run this, and here is my command, my results. I have a one sample proportion test with continuity correction. My data tells me what my data that I typed in, gives me my test statistic, fairly large one, gives me my degrees of freedom, and it gives me my p-value, which is a fairly small one. It gives me some other pieces. It tells me what my alternative hypothesis was, so compare that with your alternative hypothesis. And then it gives some things that we will talk about later. One sample portion confidence interval, same thing. That's what we just did. It actually tells it. It still uses the prop.test. The only difference here is you don't need to put the p equal to because you don't know what it is. That's what you're trying to find. And you also want to do a confidence level is 90%. So we do conf.level is 0.09. I'm sorry, 0.9, not 0.09, 0.9. That's my 90%. Again, I run that one and it comes up with that information. This time I don't need this information. I just need my confidence interval. So here's my confidence interval and my sample p-value. My sample, not p-value, but proportion value. A t-test, for one sample t-test, command is t.test, tilde variable, mu is equal to whatever that alternative, whatever the mu is equal to. This is what your HO says. Then you do alternative equals less or greater, and your data is equal to data set. The less again, greater depends on the alternative hypothesis. If you don't have a less or greater, it's not equal to, just leave that off. As an example, if you want to see if the emission levels of a new engine are less than the national average of 20, use the data set. The command would be t.test, tilde emission, data equals engine, alternative equals less, and my mu is equal to 20. There's my output. I'm a one sample t-test. My data is my emission data set, gives me my test statistic, gives me my degrees of freedom, and gives me my p-value. It then tells me my alternative hypothesis. It's good to check to make sure it is what you said your alternative hypothesis was. And then it gives some things that we're going to talk about just next. A confidence interval, same thing, t.test, your variable, your data, and then the confidence level equals C. So if you want a 95% confidence interval for the amount of emissions produced by the new engine being developed, you do t.test, emissions, data equals engine, conf level equals 0.95. When I run that one, I get my information. In this case, I don't need all this because I'm just doing the confidence level, but here's my 95% confidence level. Quick note, 95 is the default. So if you don't put the conf.level on, it will automatically go to 0.95. I just like to put it on to just remember. Two sample proportion test, same thing, because we're doing proportion, you do a prop.test. Your X's are those two values you measured from your different samples. Your N's are the two values you measured from your different sample. And your alternative equals greater or less, depending on what you have. Again, leave that off if you don't have anything. And here's an example. If you want to find If the proportion 1 is greater than the proportion 2, use a sample with n1 equal to 1000, n equal to 1200, x1 equal to 231, and x equal to 176. Then I do prompt.test, x equals c, 231, 176, n equals c, 1000, 1200, alternative equals greater. Then you can run that, and it will run a 2-sample test for equality of proportions with continuity correction. So it tells you exactly which one you've run. And here's all your information. Here's what it said you put in. Here is your test statistic. Here's your p-value and your degrees of freedom. Your alternative hypothesis is greater. If you want the confidence interval, then you just replace greater than or equal to with conf.level if you don't want 95%. And there's your confidence level. A 2-sample paired test. You need to actually mutate your data set for this one. You actually need to change it a little bit because you want to find the difference between variables. So you have to first create a new variable called difference that actually takes variable A and subtracts off variable B. So you're going to take your data set, you're just adding a column to it, so you can just use the same data set name. You're going to assign it to data set, whatever that happens to be. Then you've got your, and then you're going to mutate that. You're going to create a difference variable. You can call it anything you want, difference, whatever. And it's going to be variable A minus variable B. And then your t-test is going to be on that difference variable, whatever you happen to name it. Alternative is less or greater, depending if you need that, and data equals data set. Again, if you're not equal to, just leave that on. An example, if you want the weight of a woman before weight loss program and the weight after, using a data set diet, you're going to first mutate the data set. So we're going to have data, diet. So I'm going to use my diet data set. I just want to rename it there. I'm going to show you real fast. The diet data set has just a person before and after. I'm going to use this diet data set. I'm going to use the diet data set, and then, so remember, this is the piping symbol, and then I'm going to mutate it where difference is going to be my before minus my after. So my variables are, again, before minus after. I want to know how much weight they weighed before and after it. I'm going to run this. It looks like nothing happens, but now I see I actually have a difference column. So there's my difference column. I happen to now have that. And now I'm going to compute the data set based on that, my test statistic based on that, my p-value. Run this. And there's my 1-sample t-test, because it is basically 1-sample t-test on that difference column. My t is equal to this value. My difference, degrees of freedom is that. And then there's my p-value. If you want to do a paired test, a paired confidence interval, you still have to do the same thing. You have to mutate your data set just as you did before, and you'd run the same thing. So you'd run that. We already created that difference. I don't need to run it again. And then instead of just saying, letting it set my own, I want my confidence level to be 90%. So I'll run that with my confidence level of 90%. And there's my 90% confidence interval. Notice when I did this before and didn't specify, it went directly to the 95. I wanted 90%, so that's why I put the conf.level in there. A 2-sample independent t-test. To calculate a hypothesis test when you're comparing two populations, you need to figure out what the quantitative variable is. And what the categorical variable is the factor that you are saying they're different. So think of the factor as that categorical variable that you're making the statement that the quantitative variable being different about. The command is t-test quantitative variable tilde your categorical variable. Data equals data set. Your alternative is less or greater. Again, leave it off if you don't need to do that. As an example, suppose you want to see if the amount of calories in a beef hot dog is different from the amount of calories in a poultry hot dog. This is the data set, and I'm going to look at this one, close these up a little bit. It's my hot dogs data set. I have type, I have category, calories, and I have sodium. So I'm looking at calories. as the variable I'm working with. And type is my categorical or qualitative variable. I'm going to run this, and it runs a Welch's 2-sample t-test. It's telling me its category calories by type. It gives me my test statistic value, gives me my degrees of freedom, and gives me my p-value. It then tells me my alternative hypothesis is there truly a difference in the means between these two? And is it not equal to 0? So is that difference between these two, between poultry and beef, not equal to 0? I do want to point out that R may not do the factor the same order as you want. So if you do a not equal, less than or greater than, and you want to know if poultry is greater than beef, it thinks of beef as your first one and poultry as your second one. So you may want to put them in that order, that your first variable is beef and your second variable is poultry. And therefore, if you want beef to be more than poultry, then you would say that your alternative hypothesis is that beef is greater than poultry, that your first is greater than your second. If instead you want poultry to be greater, it does beef first, so you'd say beef is less than poultry. So just make sure you look at that and put them in the right order. Confidence interval, same thing. You're going to do your t-test on your quantitative variable, tilde your categorical variable, and your confidence level, and then you data this data set. So here, again, it did this. I can ignore all this because I'm not doing a hypothesis test. I'm doing a confidence interval, and then here is my confidence interval. All right. A chi-squared test for independence. This can answer the question about if two variables are independent or not. The process of this can be done two different ways. The first way is you actually have a data set. So therefore, you're going to create I want to call it cross tabulation. You can call it anything you want. This is the name you're giving this data set. Again, this is assigning it that way. And then you're going to tally your two variables. So you can do a tally of your variable 1, tilde your variable 2, and whatever your data set is. Again, you can call this anything other than cross tabulations. Whatever you call it, you're then going to do a chi-squared test of this cross tabulations, or whatever you called it. If you want to know the expected values, you do your chi-squared test of the cross tabulation, and then $ expected. That will give you the expected values. So you can see if they're more than 5. You can do this also if you happen to have just a contingency table. Here's where you put your row 1 in. Your row 1 is going to equal. Yeah, I used equal signs, but you can use the assigning less than and dash. And then C says combine these into one row. Make sure they're separated by commas. Row 2, keep going until you get all your rows. And then you're going to create a data table where you're going to bind these rows. And row 1, row 2, and you keep putting until you get all of your rows in there. And then you're going to do a data table. If you want to actually look at it, you can see what it looks like. And then you get chi-squared dot test on that data table that calculates it. And then chi-squared dot test data table $ expected gets you the expected values. So here's an example. This one's based on a contingency table. So we do a row 1. C is equal to these values. So I just took my row 1 values, put commas in between. Row 2, and I don't have to call them row 1. I could call this one yes, and I can call this one no. So I know a little bit more about this instead of calling it row 1 and row 2. This is a yes group. This is a no group. And then instead of calling it my data table is our binding row 1, I'd say this is yes and the no. And then I do my data table to look at it, and then I have my chi-squared test and so forth. Run that, and there's my contingency table. Again, just shows you what R typed in. And then it gives you my data table and gives you my chi-squared. This is my test statistic, my degrees of freedom, and my p-value. And then here is my expected values, and I can see that they're all more than 5. And that's it. Those are all the different inferences.